Union find, also called disjoint set union. A structure that keeps elements in disjoint sets and supports, find which set an element belongs to, and union two sets together. Use it when you have elements and relationships that connect them, like edges between nodes, and you need to know which elements are in the same connected component. Or when you need to merge sets and repeatedly ask, are A and B in the same set? We start with each element in its own set. Find of X returns the representative of X's set. Two elements are in the same set if and only if their representatives are equal. Union of X and Y merges the two sets. We pick one representative to lead the combined set and attach the other under it. Two optimizations keep everything fast, path flattening on find, and attaching the smaller group under the larger on union. The representative is one element we use to name the set. Everyone in the set shares it. Initially every element is its own representative. After a union, one of the two existing representatives takes over for the merged set. We never create a new element. This works because sameness is transitive. If A and B share a representative and B and C share one, then after union all three do too. Find just follows parent pointers to the top, and the optimizations keep that path short. Five elements, each in its own set. Every node is gold because every node is its own representative, its own root. Below we have the parent and rank arrays. Parent of I equals I for all I, rank is all zeros. Union 1 and 2. Find of 1 gives 1, find of 2 gives 2. Ranks are equal at 0, so we pick 1 as root and increment its rank. Parent of 2 becomes 1. In the tree, 2 now sits below 1 with an arrow pointing up. Union 3 and 4. Both ranks are 0, so we pick 3 as root and bump its rank. Parent of 4 becomes 3. We now have two separate two-node sets, 1, 2, and 3, 4. Union 2 and 4. Find of 2 returns 1, that's the root of the first set. Find of 4 returns 3, the root of the second set. Both roots have rank 1, so we pick 1 as the winner. Parent of 3 becomes 1, and rank of 1 goes up to 2. The two sets are merged. Node 3 is now a child of 1, and node 4 remains a child of 3, giving us a 3-level tree. A quick note, the rank-based union rule will be explained in more detail in the pseudocode section. Find of 4 starts at node 4, follows parent to 3, then parent of 3 to 1, the root. That's 2 hops. With path compression, after reaching the root, every node on the path gets its parent set directly to the root. Now parent of 4 is 1. The next find of 4 reaches the root in a single hop. Over many operations, this keeps the tree nearly flat. Without optimizations, find and union can both be O of n worst case, because the tree can become a long chain and find must follow the whole path. With union by rank only, find and union are O of log n, rank keeps the tree height at most O of log n. With path compression only, find and union are O of log n amortized. Path compression flattens the tree over time. With both rank and path compression, find and union Rho of alpha of n amortized, which is effectively constant for any practical n. Alpha is the inverse Ackermann function. Init, initialize the structure for n elements. Loop over every element. Set each element as its own parent, everyone starts as its own root. Find, follow parent pointers until we reach a root, then return it. While x is not its own parent, we have not reached the root yet. Move x up one level by following its parent pointer. X is now the root, return it. Union, merge the sets containing x and y. Find the root of each. Make one root the parent of the other, merging the two sets. Init, same as before, but also initialize rank. Loop over every element. Parent of I is I, rank of I is 0. Find with path compression. If x is not its own parent, recurse to find the root. Path compression, point x directly to the root so future finds are faster. Return the, now compressed, parent. Union with union by rank. Find the root of each. If already in the same set, nothing to do. Return early. If Rx has smaller rank, swap so Rx is always the larger rank root. Swap Rx and Re. Attach the smaller rank root under the larger rank root. If ranks are equal, pick Rx as the new root and bump its rank. Increment rank of Rx since it now has one more level.